We want to welcome everybody to our Love Your Lake, our last session. This one's called Waves on the Lakes and How Much Energy Do Boats Create? And you'll remember that Chris was here before, and he'll explain to you all the things that he did for us on our beautiful lake. I thought what I do at the very moment to get the meeting started, I'm going to throw this over to Tanya, who's going to do our land acknowledgement.
As we gather here today, we respectfully acknowledge that we are situated on the traditional territories of the Anishinaabe, Mississauga lands, and the traditional territory covered by the Williams Treaties. Kashaguigabong, an Anishinaabe name meaning Lake of Long and Winding Waters, served for millennia as an important passageway and meeting area for the First Nation peoples. We are grateful for the opportunity to live here, and we thank all generations of Indigenous people who have taken care of this land for thousands of years.
Thank you so much, Tanya. That's great. All right. Well, we're going to get started. As I say, we've got Chris Hauser here, and I'm going to throw it over to Kathy. Oh, yes, I forgot to, well, before I throw it over to Kathy, I just wanted to say on behalf of the LKO board, all the members that are here, we've got Jan and Wendy and Tanya and Kathy and Scott McPhee and Scott Sharman and Marilyn and Lance and Italo and Dale and Debbie. All these beautiful people help to put all these things together to bring to you in these seminars so that we can all learn together. So I just wanted to thank the board and specifically the Love Your Lake committee, and you know who you are, but for the great talks for this year and moving forward. So now I'm going to throw it over to Kathy, who will introduce to us tonight Chris Hauser.
Well, I'm so pleased to be able to introduce Chris. Chris is the Dean of Science at the University of Waterloo and a professor also in the Department of Earth and Environmental Sciences. His research focuses on hazards to coastlines from such things as storms and rip currents and boat traffic. And it's this latter hazard that he's going to talk to us tonight about after he's completed his 3-year study of 7 lakes in southern Ontario and how boat waves comprise the wave energy. And today we're really looking forward to seeing what results he found, especially for here, of course, but for all across those lakes. Chris.
All right. Thank you very much for that. I'm just going to share my screen fully here so that everybody can see it. And again, thank you to everyone for being here tonight and also participating in the studies that have happened over the last couple of years. And what I'm presenting today is the preliminary results from those studies that not only focus on your lake, but also all the other lakes that we included, both in the direct measurement of boat wakes, as well as the overall perception survey that we did that included all of cottage country within Ontario. Now, as some background, and I know I presented this at the last time I was here, but as some background, I began working on boat wakes back in 2009 when I was asked by the National Park Service in the United States to work at Fort Pulaski National Monument along the Savannah River and better understand how Panamax and post-Panamax ships were affecting the shoreline, and were they the reason for the very significant loss of salt marsh along this part of the coast, and what that might mean in terms of the resiliency of that coast and whether the fort, the Civil War fort, was going to be under threat. From there, I did some work and some consulting work at Lake Conway in Florida. I'll come back to this data later on because it actually is a center point for a lot of boat wake research in the United States. And there it is it's 2 small sinkhole lakes just outside of Orlando, where you have quite a bit of wakeboarding because this is the summer home to the Australian wakeboarding team. And it's 2 relatively small lakes, relatively shallow, and you've got quite a bit of wakeboarding on it, in addition to all of the other resident boats, mostly in terms of these larger floater boats, but nonetheless, you do have cruisers and other wake boats on this. And what we were doing is looking at how much energy were these wake boats producing, and was the consultant report done by the Water Sports Association accurate, and something that could we actually identify this being a cause of shoreline erosion, etc. From that particular, and in that particular study, and this is a great example, and this is Lake Conway in Florida, and you can see one of the Australian teams going by in this video. And it was generally believed, and it is common to see across lake associations and in the literature, that boat wakes are a cause of damage to infrastructure, safety to other boaters and swimmers. It causes shoreline erosion, sediment resuspension, and turbidity that ultimately leads to algal blooms. And in parts of the literature, as well as lake associations, they're identified as a nuisance and a disruption. But this is a lot of information that is anecdotal, and it's not one that actually has a lot of proof to it in terms of saying, are boat wakes as much or more than that of the locally generated wind waves? And then on top of that, do they actually have an impact? Do they cause damage? Do they cause shoreline erosion? Now, in places like Lake Conway, again, the video that is showing in the background, we know that in fact, these boat wakes are far greater than the wind waves that are generated from this site. In order to have boat wakes at the size of or smaller than the locally generated wind waves, you would have to have those wake boats moving at least 2,000 feet away from the shoreline. So this is something that actually just physically couldn't happen in this lake. And then if you look at the actual shoreline in the front part of this picture, it is hardened. And the reason why it is hardened is simply because these boat wakes are in fact a cause of shoreline erosion. Now, they've never been able to look at it in terms of sediment resuspension and turbidity and algal blooms, but that is things that we have seen on other lakes, including, before I get to the including, things that we do have evidence of where boat wakes are potentially causing shoreline erosion. This was sent to me in the fall from somebody on Go Home Lake in Ontario. And this is a small little narrow section. It does not have locally generated wind waves of any real size. And you can see the scallop shoreline here, the undercutting of the trees. And this is a spot where they were able to identify this is caused by boat wakes, and the shoreline is eroding. And other locations, such as in Florida, and particularly in the Intracoastal Waterway, we know that in fact, boat wakes, and particularly the prop wash, are able to penetrate all the way to the bottom, creating a increase in turbidity in terms of sediment concentration. But that turbidity is also evidence that it leads to eutrophication, potentially leads to algal blooms, but at the same time is responsible for mixing and overturning of that water on a cycle that it would not be normally found. And this brings me to Lake Roslyn. This is a study that we did in 2022. This is one of the first sites that we had chosen. It is just outside of Harriston in Ontario. It is a small dammed lake. It used to be a marl quarry. And so it is very shallow, maybe 2 meters in depth. And it only is about 500 meters across. And it has a number of wake boats as well as larger cruising boats and jet skis. And there is evidence here based upon the shoreline armoring of there being shoreline erosion. There are other images that I have that are a little bit more pixelated than this one, so I didn't show it in terms of water mixing and sediment resuspension. And as you can see in this picture, you get algal blooms. The perception of the owners on this lake was that they only happened after these large wake boats came in. But again, it's anecdotal, it's coincidental, it's not necessarily a direct line of evidence, and it's something that we are still working on with Lake Roslyn. But also what we do know is about where that boat is in the middle of that picture used to be a small little marsh, and that marsh is completely gone. That marsh is right in the main turning spot for the boats, and there was direct force to the vegetation, and there was a loss. So in Lake Roslyn, there was actually clear evidence that in fact boats and boat wakes were having an impact on those shorelines, on some of those shallower environments. And this kind of leading up in terms of where the studies have been going, this also brings to Whitestone Lake. And this is the lake where our cottage is. And that's actually my son in the background there. So we're out on the boat in terms of the evening, and we enjoy the water sports just as much as anybody. But this is where we started to really look at this issue in Ontario. And Whitestone Lake is just north of Parry Sound. It's on Highway 124 between Parry Sound and Sunridge. And it's a lake that is made up of largely old fault lines. And so you can see these long arms that extend out, and these are following old faults that move through the lake. So there's these relatively narrow sections, but you do have very long fetches that are broken up by these smaller islands. Our cottage is that little red dot. And during the middle of the pandemic, when we were not allowed to travel anywhere and we were not allowed to conduct field research, I was able to go to the cottage at least and drop in a pressure transducer just to figure out how much boat wake activity was there. This is the first time that question had been asked in terms of in a recreational lake. Our cottage is directly along one of the longest fetches on this lake, and it has predominantly westerly winds. So we do get wind waves that are in that 20 centimeter range during some of the strongest storms. That cottage is also on that dashed line, is directly outside of one of the main sailing lines, which comes from the marina and is on that extension between the north side and the south side of the lake. What we found, and again, I presented this the last time I met to you, but I'm using this as a build up to where we've got to in this most recent study, is that over the course of 2020, recreational boat wakes accounted for approximately 60% of all the wave energy in that year. And in fact, you can see in this top picture the frontal winds coming through and the energy associated with them. And then you can actually see the boat wakes in the second graph. The scales are in fact different. They are far greater on the boat wake graph. And you can see Canada Day civic holiday, the August civic holiday, and Labor Day holiday, you get these spikes in boating activity, even though they were happening around these times of these frontal winds that would come through almost on a weekly basis. They were nowhere near in terms of size. Overall, over the course of the summer, boat wakes accounted for the greatest amount of energy. Now you may say, well, these lakes are also experience wind waves during the spring and in the fall before the ice sets or melts, or after it melts. And that is true, but what we're looking at is during this summer period when the lakes tend to have a very diurnal breeze, they tend to be relatively calm, and they've got this well-defined thermocline. So we're looking at it at a very specific point in time. If you include some of the winter, like the fall and spring storms, you would get an increase in wind wave energy, but it yet would not come close to the total cumulative energy of just over that summer. When we look at, in fact, the reflected waves, and this is a lake that has a very rocky shoreline, and I will come back to that about how you compare these lakes with different shorelines. Our cottage is just on the very right-hand side of this particular image. You can see two boats in the picture, but there's 7 different wave trains within this image, and several of them have actually been reflected off of the shoreline and are coming back towards the center. So when you include the reflected waves, they actually account for about 80% of all wave energy on this lake. And then when you look at residual waves, this lake, typically during the summer, in particular in the morning, is flat calm. But it's in that wind in the afternoon, it really starts to pick up in terms of a lake breeze. But throughout the day, you've got almost a constant wave activity, and that's that residual wave of the waves constantly reflecting off of the rocky shorelines. Now the question is, and again, I'll come back to it, does this have an impact? Is this a problem? The answer is we don't know yet, but this at least tells us that boat wakes are adding that extra amount of energy. So this study from Whitestone, which is already published, raised 2 research questions that we decided to explore in 2022 and 2023. We took 2021 off because that was the year we could finally get to all of our other field sites, and we decided to spend the summer in Prince Edward Island doing field work. Came back in 2022 and 2023. And during these periods, we looked at how does the relative contribution of recreational boat wakes vary with lake configuration and the shoreline type, as well as what are the perceived issues with boating and boat wakes. do we see a correlation between what we're seeing in terms of energy and the width of the lake relative to that of what people believe are the biggest issues? We started that study on the Muskoka Lakes, Lake Joseph, Rosso, and Muskoka, with the support of Safe Quiet Lakes, who gave us access to a number of sites around the lake. But then from that 2022 study, we then also moved on to Lake Rosalind, as I mentioned, and then which has that 500-meter width. Here I'm going to show you a little bit of that data. And at Lake Rosalind, with only a 500-meter width at one of its largest parts without the islands in the middle, the fetch limited waves, the largest wind wave that was generated during that summer was about 6 centimeters. The largest wake heights and the predominant wake heights in that lake were about 10 to 15 centimeters. And on this particular lake, wakes accounted for 94% of all the wave energy. And it was a very diurnal cycle, that it was only during the day, and it was a moment from 7 in the morning, the first fisherman getting out, all the way till 9 o'clock at night, and then it calmed down, except for a couple of windy days. This is where they are believing that this was causing that shoreline erosion and algal blooms. In addition to Rosalind, we also worked on Otter Lake. One of the things I want to note, as I'm showing you the lake, I'm not showing you the exact location of our sensors, simply for the protection of those who actually had a sensor on their property. We want to make sure that it keeps anonymous to it. But Otter Lake, very narrow lake, very complex shape. It has some narrows, it has some bigger turning basins as well. We also worked on Lake Manitowoc around McKellar, again, just north of Parry Sound. This is a dammed lake on the Seguin River, and so it is an artificial lake. And here, what we have is rocky shorelines, but these are rocky shorelines that are in locations where the boat wakes have already eroded the shoreline back. So that particular property right here used to have a muddy, marshy shoreline and now is rocks. This is an environment where, in fact, you've got a very different type of shoreline that was not in equilibrium with any type of wind wave before it was actually dammed. And then in 2023, we worked on your lake and you would have met Ben Chittle, who designed all the pressure transducers. He started with our research group as a high school co-op student. These pressure transducers that we placed around your cottages, typically off the shelf, are around $10,000. Ben was able to make them for $100 to $150 a piece. So we've got an entire 30 to 50 of these transducers now. Ben is now finishing up his 3rd year, and he is in New Zealand on an exchange for the year. As well, you would have met Libby George, who helped work with him, as well as Abigail Carswell, who did her master's study on the Muskoka Lakes and really led the study in 2022-2023. Now, before I show you the data, I want to highlight again what makes a boat wake in terms of what its size is, etc. First thing, in terms of the size of a wake, is the speed of the vessel, the length of the vessel, how it's being run. Is it in displacement mode, which is like in this background picture? Is it plowing and pushing the water in front of it, or is it speed and planing across the surface? The size of the wake also depends upon how far you are away from the sailing line, and that changes the structure of the wave as it moves away through a process called dispersion. And so you can see this boat wake in this bottom graph here. And what happens is these waves, as they come in, have a very low frequency, very low energy, very long wave that comes in, and then it starts to increase in speed and increase in height. Well, long waves that have a great distance between crests and have a greater period, travel faster than shorter waves with a smaller period. And so the further you are away from the sailing line, the more that accordion of waves starts to spread out, which means it loses energy, but at the same time, it's going to impact the shoreline for a greater amount of time. And finally, the other control is the type of activity. Are they jet skiing and just going past really fast? Are they noodling around? Are they actually doing wakeboarding and water skiing? Each of those has a very different impact on the size of the wave that will be generated. This is an example of some of the data that came from our pressure transducers. It is about a 4,000 second record of boat wakes at 2 sites from June 11th, 2022, one in Lake Joseph and one in Lake Rosso. And what you can see is some background waves in there, and then you can see these spikes of wave data. Those spikes are boat wakes. And this blue graph with these really squiggly lines, that is a boat wake record. It's the water level going up and down and showing you as the waves are coming through and as the boat wakes come through. And then the graph that is right below it, this very colorful rainbow, is called the wavelet graph. And so the way in which we deconstruct waves, whether they are from the wind or by boats, is doing something called spectral analysis. But we're fitting sine and cosine waves to that data. That works to some degree, but as you can notice, this wave record at the very beginning, it's all over the place. It's different frequencies and there's bursts of energy. It's not consistent through time. What wavelets do is it takes those sine and cosines and basically places it on different parts of that wave record of different lengths and determines to what degree does it fit. And again, boat wakes are really long waves to begin with, and then they shorten up and get more energy. And so they have a very characteristic backwards comma shape to them. So if you look in these graphs, you'll see these kind of weird little angular features, these little backwards commas. Those are boat wakes going through, and we can actually identify them. They're a little bit better to see in this bottom graph, these backwards commas moving through the system. That tells us that there is a boat wake there. We can isolate the energy within that backwards comma and then be able to say that's the boat wake. Everything else around it is the wind wave. And so using this type of data, and you can see an example here, there's the boat wake. We then filter it using the wavelet analysis, and then we can identify times, the black blotches, where you've got wind waves, and times when you've got boat wakes, and we're able to separate the energy in that way. What we found with Lake Roslyn, again, going back to that one from in Southern Ontario, is that boat wakes accounted for about 15% of the time, but they accounted for 94% of the total energy. The boat wakes had a period of around 3 to 5 seconds, whereas the wind waves were around 1 to 2 seconds, which means with the wakes, you could actually have orbital velocities at the bottom, at the bed, upwards of 10 centimeters per second. That is enough to resuspend the marl, the muck that is on that bottom. Whereas the wind waves had periods of 1 to 2 seconds and very negligible orbital velocities. So from this, we can not only better understand what is the total energy, we can also figure out what would be the bottom velocity that would be actually induced by that boat wake. So here is some of the data that we got from the 2022-2023 data. Now, don't focus on the orange dots to begin with, focus on the gray dots. And the reason for doing that is I'm going to get to the orange here in a second. This shows on the x-axis, on the horizontal, the fetch length. This is the width of water in front of a cottage. So let's say our sensor was right here on this part of the lake. It is basically an average, a weighted average based upon the wind activity of all the distances over which way the wind can generate waves. So it's an average fetch length for every site that we placed a sensor. It gives us an idea as to how big those waves could have been generated by those wind waves. On the y-axis is the percent wake energy. So it is the percent of the wake energy to the total wave energy. So the total wave energy is wakes plus wind wave, and this on the y-axis shows you what percentage was the wakes. And what you should notice here is that across all the sites that we have studied since we began, recreational boat wakes in Ontario account for more than 60% of all of the total wave energy. Now, obviously, these are on lakes that have cottages, have boating activity. There will other be lakes that are much more constrained and restricted in terms of boating activity. They would obviously show very different here. But what this graph shows is that in general, across all the lakes that we studied, that there was a decrease in wave energy with increasing fetch length. Now that would be expected because the wider the lake that's in front of your cottage, the stronger the wind that can blow across that lake and generate larger waves. But it shows us something that we would have expected. If you take the deviation from that dashed blue line, which is basically the difference from every dot to that dashed line, what we found is that those areas that were in arms and long, narrow arms, they tended to have greater boat wake activity than would be expected, simply because those cottages, those sites, are closer to the sailing line. Bays and enclosed water bodies also had much higher than expected, or higher than that regression line. And that is simply because in a bay or a closed environment, you are simply looping around there. You're either starting up your boat and plowing out of, or you're plowing down into that bay. Where you've got really narrow sections, you tend to have a lower than expected. And the reason being is that lower than expected is that because in narrow sections, you go one way and then you go the other way. In an arm, which is much more like what you have, you then get people can actually do turning circles. It's just wide enough to turn within that environment. So you can get not only passes, you also get turns. In a narrows, you typically only get things going in one direction. And that's one of the reasons why through your narrow section, while you're closer to the sailing lines and the boat wakes tend to be greater, the boating activity is typically less because people can't spend as much time there and they can't be going as fast. Whereas in open sections, it's a little bit below the line too, because you're further away from all sailing lines. So what we found is that in general, across all of Ontario, boat wake energy is directly related to that of the fetch length and gets smaller as you increase the fetch length, simply because boats can be out in the middle and wind waves get stronger. Everything worked except your lake. Of all things, it was your lake that was backwards to all of this. And your lake is the orange dots. Now, I only am showing 5 here, simply because one of our pressure transducers got flooded. So we don't have full data set from that. We've got a partial data set, but I don't want to include partial and full data sets. So when we include these 5 data points, you actually got a weak, but still statistically significant increase in wake energy with larger fetch lengths. So that suggests that the people who are in the southern section of the lake and in the northern section of the lake have much greater than would be expected, and in fact, more than other lakes like Lake Muskoka and Lake Rosso. And the reason is that you've got a constrained environment in which this boating activity can occur. Typically in the narrows, you have to go slow, you have to do a pass. Where in these wider kind of arms, you actually get people have the ability to turn and you can concentrate your activity. So your lake, by its configuration, by its way it's shaped with that little narrow band stuck in the center, you have an opposite relationship to the other lakes that we studied during our time. Now the question then comes down to across all of the lakes that in fact boat wakes account for more than 60% of the total wave energy. But is it more energy in terms of we're just adding on top of the wind waves, or is it more energy because we're adding much bigger waves? And so we did 2 tests. We did what's called the Kolmogorov-Smirnov test. It looks at whether 2 non-normal distributions are significantly different. What I've shown you here is the cumulative percent graphs for both wakes and wind waves. And what it shows is that boat wakes not only are within that same part of the distribution as wind waves, they add far greater wave energy. So I've taken that cumulative one and shown you essentially a stylized version in the little inset graph. The red solid line is the boat wake distribution, and the dashed line is the wind waves. So on a place like Otter Lake, which has an effect, and this particular site had an effective fetch of only 190 meters, boat wakes not only were a much greater contribution to the total wave energy, it represented much bigger waves than could ever be generated by the wind waves. So if there was going to be an impact, and again, I'm not saying that there was, but if there was going to be an impact, this would be the type of site where you would see it. Now, if I take one of the site on your lake with the longest fetch, again, based upon all the different wind directions that come through, it was about 2 kilometers, and it's looking up one of those long arm sections. Here, boat wakes still account for greater than 60% of the total wave energy, but that wave energy is much more similar to that of the wind waves. It still provides bigger waves than would be expected by the wind, but it's not that much bigger compared to what you would get at Otter Lake. So there's 2 types of things that boat wakes are doing. One, adding more energy, but also adding more energy because of much bigger waves. And I know you know this because you're sitting up your dock, and I see this all the time. But again, this is the first time that we've been able to piece these pieces together in an objective way. So this raises the question, so how much different are they? So what I have here is the fetch length, again, along the x-axis, and the y-axis is the ratio of the wake height, the average wake height, to the average wind wave height. And what we find is that in the very small sections of the lake, that your boat wakes are up to 1.6 times greater than that of your wind waves on average. Whereas if you get to these larger sections, the boat wakes are there, but they're only just above 1, which means they're just slightly bigger. And that's the way to interpret those 2 graphs that I had shown you before. Wind waves in the first one, which is like that Otter Lake one, might have accounted for 20%. Wakes are about 80%, but 80% energy of much greater energy. Whereas in a longer lake section, wind waves may account for 40%, wakes only 60%, but there's similar distributions, and wakes still provide bigger waves, but not that much bigger than the wind waves behind. So this goes again to what you would expect when it comes to the length of that lake, but also has it's important when we start to think about, does it have an impact, and what might be done to try and minimize any damage that might be occurring. I will explain that vertical dash line towards the very end of the presentation. So when you compare wake energy across the different lakes, Roslyn, Whitestone, Muskoka, Yours, Manitowoc, and Otter, Yours and Muskoka, and the entire Muskoka lake set, had the lowest of what we had measured, but it was still in that 70% range on average. So in your lake, at least at the sites that we sampled, which were representative of the different widths and configurations, boat wakes account for about 70% of the total wave energy being reached at the shoreline. Boat wakes, if you also look at it in terms of time is an opposite relationship because of that dispersion, because the waves start to separate. The long waves travel faster than the short waves, and they begin to separate like an accordion expanding. And so for the very, very small lakes, wakes accounted for a relatively small amount of time, but as you got to be larger and larger, they then started to get longer in terms of the amount of time that they were impacting the shoreline. What we also found is that the deviations across all of our lakes tended to depend upon the type of environment. The biggest deviations were bays and enclosed environments. So I mentioned Lake Roslyn before. Lake Roslyn is this top dot right here, just above that 500-meter mark. That is so high because Lake Roslyn is just a circle, and all you can do is go around and around and around. So in bay enclosed environments, you get a lot of time, more time than expected, based upon the number of boats, because there's just nowhere for that wave to go. Whereas on smaller lakes that may be arms or narrow sections, they typically have a slightly lower amount of energy. The number of wakes that you also get also depends, kind of varies in that exact same period. So it was a surprising graph, and I had to do this one several times because what you have on the y-axis is the average number of wake waves, individual waves in a wake per hour. And so in places like on your lakes, on some of your sites, on average, we were recording up to 120 individual wake waves over the course of that summer on average per hour. That's a lot of waves. It was shocking when I actually saw that number. I see a chat came up. I'm going to just wait for the to
Yeah.
the very end to be able to answer some of the questions. I want to make sure it wasn't something in terms of a clarification on a graphic there.
Yeah, no problem. Yeah, anyone at any time, please feel free to insert your questions in the chat and we'll address them at the end. Thank you, Chris.
Right. And part of what determines the number of wake waves, again, goes to the type of the shoreline, and it's more this kind of how you are noodling in the environment. Now, to add this, I'm getting back towards to your lake, and that bottom line is that we did the perception survey. We wanted to better understand what we were seeing, similar to that of what people were saying to us when we were asking those questions. Now, we did this perception survey, and it was Ava Cascara who ran this survey. It was an undergraduate student who did her thesis on this particular topic, and she had 635 respondents from across Ontario. There were other respondents from British Columbia and the United States. We did not include them because we kept it just to the cottage country environment of Ontario, because that's where our research ethics board was actually there. So when you look at the largest perceived change that people have noticed over the last 5 to 10 years, what you find is that, in fact, the responses also vary with the fetch length. So this fetch length was on the x-axis is essentially the width of the lake, and it's based upon, you told me what lake you were on, we digitized that lake, and we figured out what was the average fetch length for that particular lake. Your lake is between 750 and 1,000 meters in terms of that average fetch length. And what we did is we put it there. So that's that circled graph. What we find is that the impact of boat wakes decreases with fetch, but at the same time, the amount of boat traffic kind of dips down through the middle parts and increases on both ends. It doesn't really show a very, very clear relationship, but we also notice that water quality and shoreline change are identified as the biggest impacts or perceived impacts on the smaller lakes compared to that of the larger lakes. Again, when you think about those distributions, this would make sense that, in fact, on the smallest lakes, you're going to have not only more wake energy, but more energy in the bigger waves, which can cause changes to water quality because you can penetrate to the bottom and you're going to erode the shoreline, as well as the level of safety because your wakes are concentrated. They have not yet dispersed, whereas in the larger lakes, they tend to spread out. When you then look at what was the biggest impact that people believed wakes were causing, what we find, and this is please note that the y-axis is upside down. We purposely kept reversing our axes so that people would have to read the question and pay attention to what they were answering. But what we found is that, in fact, shoreline erosion and was found to be of greatest impact on these smaller lakes. It typically got then larger, with the exception of this 1,000 to 1,250 meter area. It tended to be less impactful. Again, it makes sense when you think about those distributions. Not only do you have more wake energy, you have more of bigger wakes in terms of providing that energy. But again, and you start to see this variation that the overall impact is believed to be greater in the smaller lakes. And that suggests that people are observing something that is telling us that there is an impact. When we then ask the question, like, tell us about it. What's going on with wakes? What did you notice? What's the biggest problem in terms of wakes on your lake? The majority, 66% of all respondents across the 635 respondents that we had, noted issues with the type of boats, their operation, and lack of experience. And you can see some examples here, and I'll be giving you these slides later on. You also have the video, so you'll be able to read them in a little bit more detail. But they're talking about behavior and use rather than an actual impact. When we then started to, when we looked through the data and we coded all 635 responses, we looked at what they were describing as the issue. What we noticed is that only 9% of all respondents noted shoreline erosion, only 3% noted safety, and only 3% noted damage. This doesn't mean that it's not present, because people on the small lakes are saying, yeah, this is a problem. What it means is that they didn't have direct, clear evidence to provide us. They see something, they're perceiving something, they believe something, but there's not necessarily a direct evidence that says that that in fact is the problem. And when you started looking at what were some of the ones that were brought up, it was things such as boat wakes are getting bigger and it's causing me to change my filters. The lake is less clear than it used to be. Swimmers are being rocked by the waves on passing boats. Your lake. I've had to do $500 in dock repairs. One of them, I just spent $30,000 protecting the point of our property. And another one on Lake Muskoka, it cost me over $25,000 to undo the damage from the large wakes. Again, that's not direct evidence that that the wake was in fact causing it, but it tells us that they are seeing, that they provided us direct evidence that there's something that they were seeing a cause, not to say it directly was. I want to make sure I'm clear on that. When we look at the actual descriptions of shoreline erosion, almost all the responses, all 9%, came either from Lake Roslyn, your lake, or Joseph. I can't figure out Lake Joseph because it's a rocky lake. I can't figure out how you're eroding granite. But for your lake and Roslyn, different types of shoreline, and in fact, we start to see evidence where in fact people are saying that in fact there's erosion, there's damage to habitat, etc. So your lake was the one that in terms of had the greatest number of people who provided evidence and direct descriptions of erosion, damage to habitat, and to safety. Now, the reason why your lake and Roslyn had the greatest number is because of the type of shoreline. Most of the lakes in cottage country are on the Canadian Shield, and they have very rocky shorelines. Now, yes, like that Go Home Lake, you did have some rocks that used to have vegetation that extended down to the water in these very protected environments. There's erosion there. There was erosion in that Manitowoc example that I gave you previously. But those are in areas that have only just started to experience boat wakes. So this raised an interesting question, because with the exception of yours and Roslyn, which have much more sandy, muck, and unconsolidated shorelines, most of them were rocks. And so I stood there looking at my own shoreline, and I wondered, has the damage already been done? Because boats have been on my lake, Whitestone, for almost 30 plus years. So there may have been habitat, there may have been erosion, but it's long gone. What we have is a rocky shoreline. I don't have an answer to that, and that's going to require a historical analysis. And maybe this is what I throw back to, I can't think of the organization that you have with Trent right now. This is something I throw back to you to actually say, hey, this is something that we should be looking at, going back through historical imagery, and can we see evidence where shorelines have been eroding that is independent of shoreline development. So in some of these other environments, why erosion may not have come up is simply because they're rocky, but you might still have an impact associated with damage to infrastructure, sediment resuspension and eutrophication, as well as temperature and mixing. Here on your lake, there were 30 responses. So out of 635, 5% of all responses came from your lake. That doesn't include any of the surrounding lakes. And what we got is some of the ones I've shown you before: loss of habitat, decrease in natural habitat, excess speed in river, wake boats, etc. Boaters swooping into the large bays. You can read through and go through this. We did have 2 responses out of the 30 that said that boats and boat wakes had no impact, and it was pretty well a short line like that. That's why I'm just saying it verbally. So in fact, we are, what you have is 28 out of 30 respondents for your lake identified that boat wakes as being an issue, but only a small percentage actually said that in fact you had direct evidence for that. Again, as you go through, you can look at this. I do apologize if you see spelling mistakes and made up words, but this is a direct quotation from the survey. Preliminary results, I'm getting here towards the end, and I see there's 4 questions in the chat. The preliminary results are that boat wakes represent a significant source of wave energy in these fetch-limited environments of cottage country. The percent wake energy and the time are related to the fetch length, and it varies with the shoreline type. Is it a bay, a narrow, etc.? But across all the respondents, we had very few clear examples of shoreline erosion, damage to infrastructure, or safety. And what we saw in the vast majority of responses was that operation, noise, courtesy, and conflict were of greatest concern. That doesn't mean that there aren't examples. They just didn't provide clear ones that actually said, I had to do this amount of shoreline change. I've lost this amount of shoreline. I've had to do this much reconstruction. So what we need in terms of further study is definitions for impact and tolerance. I'm going to get to this one because this is really the key question that you have to ask. The next one is collect current and historical evidence of shoreline change, damage to infrastructure and habitat, and degradation of water quality. And please send them directly to my email. We're going to start to collect that and better understand what those types are and maybe do a broader survey. And then also look to direct measurements of wake impact on water quality, that temperature inversion, the overturning and mixing, and potentially sediment resuspension. We're going to do a test project at my cottage because I can watch it for 2 weeks and just sit there on the dock and do that, with 2025 being the real study. But definitions of impact are important. So I'm going to go back to these idealized graphs. The results are that wakes are larger in terms of in terms of the size of the waves, depending upon the fetch length, and provide greater percent of the total wave energy. But what's not clear is what level and or frequency of wave energy actually has an impact. Does simply doubling up the number of wind waves make an impact? Is that what eroding the shoreline? Does that have an impact on infrastructure? Or are those environments, the shoreline and the dock, tolerant to what would be the natural wind wave? And is the damage being caused by the tail, where these got these very large wakes that come in? And the reason for raising this question, because I have seen on cottage associations 2 focuses. One, to limit the amount of boating activity, and number 2, to limit the size of the wakes. Those are 2 very different questions. So in scenario 1, which is where you want to limit the amount of boating activity, what you have to do is simply decrease how many boats are traveling on your lake. And in order to do that, that's going to take almost 50% of all your boating activity would have to be shut down. That's a problem. It's a difficult one in which to enforce, and there's no regulation associated with that. But number 2, do you reduce it by 75%, 50%? We don't have an answer because we don't know what causes damage, what causes shoreline erosion, etc. In the scenario 2 is where you limit the size of the wake. And this is one that I know is being worked on in Minnesota. It's something that Save Quiet Lakes has been interested in, that maybe there's a distance from the shoreline that boats should not be able to get within. And by doing so, we can reduce the size of the wake. But how much do you have to reduce the size of the wake? Do you just simply reduce it to the size of the largest wind wave that can be generated? Is it half the size of the wind waves? Is it 5 centimeters? Is it 6 centimeters? There is no clear answer to what that is. What you have to do is define, A, that a boat wake is causing this impact, and a boat wake of this size, this frequency, causes that impact, and we want to minimize that. That is something that every cottage association I have spoken to has a different definition of. Every jurisdiction does. So to say 1,000 feet is a limit is somewhat arbitrary to actually say that. And that represents a bit of an issue as we get into how, if there was a regulation ever done, how that could actually be done. So let me pick scenario 2. And this is where I'm going to be ending my talk here. In scenario number 2, let's say you wanted to reduce the size of the wakes that are reaching the shoreline so that they're no bigger than the largest wind wave that can reach that shoreline. On the really tiny lakes, you get wakes that are massive, 1.6 times that of the wind wave. Whereas on the large lakes, they're almost near the same height. They're already close to that maximum wave energy. So what we did is we took our data, knowing what our sizes of our wakes were and our waves were, and then what we did is we combined it with that of what you would actually, what the Water Sport Industry Association found for a variety of different types of boats. And this comes from Lake Conway, the one in Florida. And they had wake surf speed, wakeboard shallow, and cruise shallow. And these represent the upper, the middle, and the lower bounds in terms of these curves, which is how that boat wake dissipates away from the sailing line. And what we did is a back of the envelope calculation that said, we want to reduce our boat wakes to be only 3 centimeters when they reach the shoreline, because that is the average wind wave height that we measured over the summer. And by doing this back of the envelope calculation, on the lakes that we studied, wake surf boats in deep water would have to be 404 meters from the shoreline. Wakeboard shallow would be 247 meters, and cruising in shallow water, so probably like 2 to 3 meters deep, would have to be 200 meters from the shoreline. In order to reduce your wake to the size of the average wind wave across the lakes that we sampled in 22-23. 3 centimeters is just the average wind wave height. It's that kind of that dash line equivalent. 3 centimeters has no direct reason for 3 centimeters. We just picked it as the average. What you have to be able to do is figure out which height actually causes the impact, whether that be to infrastructure, to resuspension, or to shoreline erosion. Once you have that, we can work through the data and say what would be those sailing lines. But I can tell you, on your lake, a wake surf in that deeper part of your lake, 400 meters, it's pretty well down the center line, do a perfect circle, and back down the center line, but obviously not getting towards the end of the bay. If you then take that data and put it across all of our lakes, in order to have any wake less than 3 centimeters, you would have to have no boating activity on lakes smaller, with fetches smaller than 400 meters. That would be nearly impossible in cottage country. So this represents the dilemma. Are they a problem? What's that impact level? And what would be required to reduce the size of the wake and or the amount of energy? So with that, I am going to open it up to any questions that you might have. And I see a bunch coming into the chat.
Yeah, thank you. Thank you so much, Chris. I mean, very informative and quite interesting. I'll just start with the first question that's there. What's the average bottom line for the Lake Cache?
So what it does is it says that about 70% of your total, I'm using average or bottom line, meaning not depth, but rather what is the impact?
Right.
About 70% of the total wave energy on Lake Cache is associated with boat wakes. Because of the size of Lake Cache, you've got some sections where boat wakes are within the distribution of your wind waves, which is in those wider sections. But in your narrower section, boat wakes do represent a significantly larger source of energy than would be ever expected by the wind waves, just simply because you got a small body of lake. The question then comes down to that bottom line is this last slide, and why I brought it back up is because we don't know what the bottom line is. We don't know what does impact mean, and what does impact Is it the size of the wave, the frequency of boating activity, both? Do you want to get them down to 3 centimeters, etc.? So the bottom line is that boat wakes do represent a major source. We need to figure out what is that true measure of impact that it may or may not be having. And I see
Thank
the
you.
next one. Ian, thank you. Ulinks. I could not get that name out there.
Yeah, Ulinks. I was just going to mention you. Yeah, this is a good question that we can ask that you've presented to us to Ulinks, and they have the relationship with Trent. Another question is, Chris, which level of government has the authority to regulate the size of motorboats on lakes in Ontario?
That, my understanding, is largely federal, but is something that is outside my scope. I keep out of the governance side of all this. I'd be happy if anybody else in the audience could answer better. And I would say Safe Quiet Lakes probably has the best information on that. They've been working directly with all levels of government.
Well, that's a good reference or resource that we can tap. Another question is, can you compare your wave data from boating lakes to non-boating lakes that have similar varied fetches to determine environmental impacts of boating?
And you're exactly right, Kathy. And that's one of the things that we are interested in looking at when it comes to turbidity, overturning, etc. Can we find 2 lakes of similar configuration, size, and location that we can say, here's our control lake and here is our non, to be able to look at what it's doing in terms of the water column, but then also more historically, what has happened to the shoreline and what could we have expected the shoreline of the boating lake to have looked like previously. But you have to find 2 unicorns, and that's the tough part. We're still looking for that.
One last question says, Chris, I've watched your previous videos. Thank you for your work. And in those videos, you admit to enjoying boating, water skiing, jet ski activity. What impact has this study had on your own water sport activities?
That's right. So it comes down to the way in which we use the lake, in terms of the way we are going down the lake. So this one shot, that's my son driving the boat there. I apologize, he doesn't have a life jacket on. I didn't notice that until I started showing that presentation. But we're going down the center line. We're keeping within that the maximum distance to any of the adjacent shorelines, and we make sure to get up onto planing as soon as possible. They have tried wakeboarding. We typically are water skiers, and we keep it at a relatively fast rate. So it has changed the way in which we do it, but we only do it for 3 days each summer.
There we go. Thank you. One last question that's come in. What types of studies are necessary to evaluate wave impact on nesting and erosion?
So one is that you would have to have a lake where, again, this goes back to, has the damage already been done? And if I look at my lake, I couldn't tell you if there is erosion happening because it's a rocky shoreline, but is it a rocky shoreline because there has been boats there for decades? I don't know. I get myself caught into this kind of circular argument. So you'd have to find a spot where you could then be able to look at relatively unconsolidated site, look at it through history with the boating activity on that lake, and or watch it through time. And so your lake does represent an opportunity. If you've got a sandy beach, a muddy environment, one of the things that you can do, and you want to be very careful with this, is it's called a depth of disturbance bar. You take a piece of rebar, make sure you highlight it and paint it, and it's in shallow enough water that nobody's actually going to hit it. But you put it in that water and you put it into the ground and you put a washer on top of it. So then as you can then measure the depth, that gives you an idea as to whether the bed is eroding over the summer. And if there is resuspension, that washer slowly works its way down deeper and deeper or gets buried by material. So there's ways in which you can do small little surveys of that, and I'd be happy to speak to those by email and kind of help with people doing some very simple studies in which to look at, are there shorelines being affected by it? And again, it's when I did the stuff up in Savannah, I'll just go back up to the picture here in Savannah. What you can't see are these depth of disturbance rods that I had across the surface. I think I'm standing right on the line. So we were able to look at the mud, and then we had depth of disturbance lines directly into the cliff face. So we could look at the rate at which it was eroding. In terms of nesting, that would be something you would want to consult with an ornithologist. I'm not an expert in nesting behavior, and I wouldn't be able to tell you a good nest from a bad nest or a disturbed nest. So I wouldn't want to come up with that. But shoreline erosion, if you send me a direct email, again, I'll put my email directly into the chat. I'd be happy to answer any questions that people have that follows this presentation.
Beautiful. I don't think there's any other questions that have come through the chat. Scott, do you want to, Scott McPhee, just remove the spotlight so those that want to there we go, can turn on their videos if they so wish. And so Chris can see all these beautiful smiling faces. I don't think there is any more questions. But I think I'm going to throw this over to Jan now, just to sort of conclude our Love Your Lake session.
Before Jan kicks in, though, I know we sent 3 questions that a gentleman sent.
Yeah, and so Chris answered those 3 questions. Thanks,
Okay.
Dale. Already in his talk. So the question of what fraction of a large wake is on it. What is one? Oh, when a wake crosses a wake from a boat going in the upstream, is there any attenuation?
Okay, that one caught me off guard because I had never thought of that before, but it doesn't have an effect. They pass right through each other unless they cause each other to break in that moment. So sometimes when you get 2 big waves hit each other, they will crash. That does dissipate some energy, but not a lot. You do have them just pass through each other in the medium.
Right. And the other one was, how do periods of boat wake on weekends compare to stormy days on the lake in terms of shoreline impact? And I think
this is we're looking at the cumulative piece to all of this, and overall that boat wakes do have that greater energy. And then the third one, what is that sailing line distance? And that's why I added that very last slide about, is it 1,000 feet? Is it 400 meters? Is it 800 meters?
Mm-hmm.
And yet the question of impact and damage, I have not found good evidence for as to what would people use, and I'd be interested to hear from people after this talk as to what they consider to be damage and impact that is measurable.
Beautiful. Jan.
Okay, well, here's the big thank you one more time, Chris.
Thank you.
Thank you very much. It was a very informative presentation. You've probably left more questions in our mind than answers, solid answers anyways. I hope that you will remember Lake Kashagawigamog when you're looking for study participants in 2025. I think we would be very interested in participating in that. And we will certainly engage with ULinks from Trent University with the historical evidence on shoreline erosion. I'm pretty certain we can come up with some. There are many property owners who are longtime owners that probably have photographic evidence that we can work with, and if not, the Historical Society. So that's something we can pursue in the future. So thanks again for your time in
preparing
this and presenting to us. Well, big round of applause.
Thank you.
Virtually.
Hey, Chris.
I'd like to thank everyone for attending tonight, as well as for the other Love Your Lake sessions this spring. Special thanks to Kirsten, our moderator, who no longer has obligations as a board member, but continues to volunteer for this particular project. Thanks, Kirsten. And
Thank you, Kirsten.
thanks to the board for creating Love Your Lakes. And it takes about all 10 of us to get it together. We're getting better at it, but it is a bit of an organizational project for us. Just a quick reminder to people, if you haven't renewed your LKO membership, it's a mere $35. A lot of people kind of forget this time of year. If you've never joined, it's a really good bargain for $35. We do a lot of work on behalf of the lake, including this Love Your Lake session. We are interested in any further questions regarding Chris's presentation tonight. If you have any, Chris has provided contact emails. You can reach out to Chris directly. Likewise, if you have any ideas for next year for the Love Your Lake, we are intending to run the series again next spring. So please submit any ideas that you would have for something you'd like to learn about to the secretary at LKO. You can utilize the contact information on our website. Just a reminder that the annual general meeting is on Saturday, June the 22nd. The doors open at 9. It's usually a wonderful social half hour. Meeting will start at 9:30 promptly so that we can all get out and enjoy a nice June day, we hope. And a reminder that Cash Art on the Lake is August the 10th. So on that note, I think that's all of my messages. Thanks again, Chris, and everyone who attended.
Yeah, thank you. Great to see everybody. Have a great rest of your evening. Thanks again, Chris.